An intro to Rlc circuits. So an Rlc circuit is a basic closed electrical circuit. That contains a battery, a resistor, an induction coil, and a capacitor. Along a closed wire loop. So here we have sort of a diagram of our basic Rlc circuit. We have our battery or generator, which provides impressed voltage. Typically denoted by E of T. We have our resistor, which provides resistance, R. We have our induction coil, which provides inductance, L. And then our capacitor provides capacitance, C. We have electrical current moving through the circuit, and the direction of positive flow will move from positive to negative. So this is our current flowing through. So I'm just going to summarize sort of what we have seen so far. So we have resistance, or our impressed voltage, E of T, is measured in volts. That's what is provided by the battery. Then we have our resistance from the resistor. Our resistance is R ohms. Update my screen. We have our resistance equals R ohms provided by the resistor. We have our inductance of L henries provided by our induction coil. We have our capacitance equals C farads of our capacitor. In addition to that, we have a current equaling I of T that flows through the circuit. At any time T. I should have said the current is measured in amperes. And then we have our charge, which is Q of T, is held by the capacitor at any time T. This is in coulombs. So this is the charge held by the capacitor at time T. So this is all of the variety of numbers and functions that we will be working with. The resistance, the inductance, and the capacitance are all positive constants. And then our impressed voltage, our current, and our charge are all functions of time. So the current and the charge are related to each other. The charge and current are related. The charge is essentially the initial charge plus the total current to pass through the capacitor or the capacitor. We wind up getting that the charge Q of t is just the initial charge plus the definite integral from 0 to t of the current I of x dx. So we're essentially looking at the total current to pass over a period of time through the capacitor. So this is our charge. What this means then is similarly, we get that Q prime is Q prime of t is just I of t. So we have a relationship between the charge and the current. Now we want to look at a relationship between all of the various components of our circuit. So it turns out by Kirchhoff's law, the impressed voltage is equal to the sum of the voltage drop across each of the other components of our circuit. So across the resistor, induction coil, and the capacitor. So what we need to know then is what are the voltage drops of each. So if I call the voltage drop just V labeled by R, I, and C, we have the voltage drop across the resistor plus the voltage drop across the induction coil, which I'm just going to label VL, plus the voltage drop across the capacitor, VC. This is equal to our impressed voltage E of t. So we need to know what are the voltage drops. Our voltage drop VR, the voltage drop across the resistor, is simply the current times the resistance of the resistor. So equivalently, since Q prime was I, our voltage drop across the resistor is just the resistance times Q prime. So we have our VR as resistance times Q prime. Our voltage drop across the induction coil, VL, This is given by the inductance times the derivative of the current. So since the current is the derivative of charge, the derivative of current would be the second derivative of charge. So our voltage drop across the induction coil is the inductance times the second derivative of the charge, Q double prime. And then finally, our voltage drop against the capacitor. Voltage drop across the capacitor, VC. This is given simply by taking the charge Q and dividing by the capacitance. So what we get then is plugging this in to our equation VR plus VL plus VC equals E of T. We wind up getting inductance L times Q double prime plus resistance R times Q prime plus 1 over C times Q is equal to our impressed voltage. So I swapped the order of the inductance, the voltage drop across the induction coil and the voltage drop across the resistor, simply because I wanted to put my derivatives in decreasing order. But from here, we do have a second order linear differential equation with constant coefficients. So this means that the charge in an RLC circuit is modeled by a second order linear ODE differential equation with constant coefficients. Furthermore, the initial conditions Q of T naught equals Q naught and Q prime of T naught equals, I'm going to be sloppy and do Q naught prime. This Q prime of T naught is actually simply our current, right? Since we had the Q prime was equal to I. So this is just I of T naught. And so we often just write this as an I naught for our initial current. So we have the charge in an RLC circuit is modeled by the IVP LQ double prime plus RQ prime plus 1 over C times Q equals E of T, with initial conditions Q of T naught equals Q naught and I of T naught equals I naught. So we have, in this case, initial charge and initial current is usually how we will be given that information. And then you just need to keep in mind that the initial current is actually the derivative of, or the initial derivative of charge. So this is our basic RLC circuit. We will do some examples in the next videos.